All right, chemists, welcome to another installment of Ralston Valley High School Chemistry's AP Chemistry Lecture Series. In this lecture, we're going to be looking at Chapter 14's discussion of the acid-base properties of salts and other species. This is the final lecture in Chapter 14. Let's go ahead and move forward. All right, over the last few lectures, we've been talking about the properties of acids and bases, and what we're going to start off our conversation here today about is discussing the acid-base properties of some things that don't immediately look like an acid or a base to you at first glance. So if it doesn't just like scream out, here's the acidic hydrogen that's going to be lost like a species like HCl, how is it we can recognize that something might behave in an acidic or basic fashion? The first one we're going to look at here is the acid and base properties of oxides. And as it turns out, we've given you two rules of thumb to follow here. The first being non-metal oxides, when dissolved in water, produced acidic solutions, whereas conversely, metal oxides dissolved in water produce basic solutions. Let's take a look at a couple of familiar examples of these two types of interactions between oxides and water. The first of which here is example 1, in which we're going to ask you about carbon dioxide gas being bubbled through water. We're going to go ahead here and write a balanced chemical equation describing this reaction. So starting off with a little bit of nomenclature here, we got the binary covalent compound carbon dioxide, CO2, and we are bubbling that through water, familiar H2O. And if we look at this reaction, it looks more or less like a synthesis here, in which we're going to combine together the reactant species here to form the product here, which in this case is going to be H2CO3, which you'll recognize from our nomenclature earlier in the year as a species which is a ternary acid that is made up of hydrogen plus a non-metal, in this case carbon, plus oxygen. So this particular ternary acid is the parent acid of the family. It is called carbonic acid, H2CO3. So we recognize here that bubbling carbon dioxide through water, carbon dioxide being a non-metal oxide, we generated an aqueous solution of carbonic acid, that is, an acidic solution. This should be a familiar reaction to you, as it is the reaction which generally we see in beverages like club soda. It's what gives it club soda that kind of acidic bite to it in carbonated water. So example 1 taken care of, pretty easy peasy there. Moving on now to example 2. In example 2, we're going to go ahead and dissolve calcium oxide in water. And again, we're being asked to write and balance a chemical equation describing this reaction. So nomenclature first here, we've got calcium oxide. Calcium is an alkaline earth metal, therefore it's going to lose its 2 valence electrons as it forms a compound. And we're going to have a calcium with a +2 charge. The oxide ion is oxygen with a -2 charge on it, as oxygen is going to pick up 2 electrons to fill its octet. So the formula here for calcium oxide is CaO, and we're combining that with familiar compound again, water, H2O. And in this instance, we are going to be producing a basic solution, and again, this is going to be more or less a synthesis reaction. If we combine calcium oxide and water, combining those together, we're going to have the compound CaOH2, that is calcium hydroxide, as a product. Now, before we move on, recall that the AP test is going to most commonly ask you to write net ionic equations describing these reactions. So for this net ionic equation, I want to recognize that calcium hydroxide is one of our list of strong bases. And as such, calcium hydroxide will exist to a large degree as dissociated ions in solution. So we're going to go ahead and rewrite this equation now, which will be calcium oxide, CaO, plus water, H2O, forms as products the dissociated calcium ion, Ca2 positive, plus 2 hydroxide ions, that is 2OH negative. And again, we recognize in this instance we have formed hydroxide in our solution, implying therefore this is now a basic solution. And a good way to remember this is just to remember that the word alkali or alkaline, which refer to those metals in group 1A and 2A on the periodic table, literally means basic. So we can remember that those metals or metal oxides tend to form bases when interacting with water. All right, now having explored the acid-base properties of metal and nonmetal oxides, we're going to go ahead and move on to something which we were introduced to way back in first semester when we investigated the properties of complex ions. In particular, we're going to be looking now at the acid-base properties of metallic ions dissolved in aqueous solutions. As it turns out, the metallic ions, that when we dissolve them in aqueous solutions, are a little bit more complex than we initially consider them to be. In particular, if we have a highly charged metal cation dissolved within an aqueous solution, in general, that will form an acidic solution overall. And that seems at first glance to be a difficult thing to justify when we think about, again, a acid being a proton donor. Thinking about a simple metal cation by itself seems almost impossible to justify why we would see hydrogen ions forming in solution in that case. However, remembering back to first semester, a hydrated metal cation in solution really is going to be more accurately described as a complex ion in which water is acting as the ligand, forming that coordinate covalent bond to the metal cation by donating one of the electron pairs from the oxygen atom within a water molecule. And in particular, if we look at the diagram that we have right here of this aluminum-3 cation, you'll note here that that aluminum-3 cation is diagrammed here as having bonded to 6 water molecules, forming this hexa-aqua aluminum-3 cation, this complex ion within an aqueous solution. And if we treat a dissolved metal ion in its more accurate sense as a complex ion, again with a water ligand, we can recognize that the very large positive charge present on that aluminum cation there is going to draw electron density towards itself. The net effect of drawing this electron density towards itself is that those electrons in the water molecules are going to get drawn towards the positive charge on that central metal ion. And as such, we're going to polarize and then weaken the oxygen to hydrogen bonds present within the water molecules themselves. And as such, that's going to make those hydrogens more effective hydrogens that could be donated via a Bronsted-Lowry acid-base interaction with another water molecule within the solution. So, long story short, the large positive charge draws electron density away from the oxygen-hydrogen bonds, weakening those bonds, making the hydrogens more partially positive and therefore more effective hydrogens to be lost in an acid-base interaction. And for that reason, we can see then that solutions which contained dissolved metal cations with large positive charges, like say for example a solution of aluminum nitrate or ferric chloride containing the Al3 positive or Fe3 positive cations respectively, would likely generate an excess of hydrogen ions in solution and therefore have pHs significantly below 7. And important to note here, this effect is more pronounced the larger the charge on the metal cation, given that the larger the charge on the metal cation, the greater the ability of that metal cation to attract electron density towards itself. And as such, we would consider a solution of, say, ferric nitrate or aluminum nitrate to be a likely acidic solution, whereas a solution maybe of sodium nitrate, where the sodium ion again only has a +1 charge, would not exhibit acidic characteristics because that sodium ion does not have a sufficiently large charge to meaningfully draw electron density towards itself, and as such, it doesn't significantly weaken the oxygen-hydrogen bonds within the ligand water molecules in, say, for example, a hexaqua sodium-1 complex ion. All right, and at this point we arrive at probably the most important of our slides for this particular lecture. That is, we're going to be looking here at the acid-base properties of salts. This is by far AP Chemistry's favorite type of species to ask you about on both multiple choice and free response questions. And understanding the acid-base properties of salts is a complex endeavor because to determine the acidity of a solution containing a dissolved salt, we have to look at any potential hydrolysis reactions that might result from interactions between the water molecules in the solution and either of the dissociated ions present from the salt in the solution. So we're going to look at 4 different cases here and fill out our table in terms of the acidic or basic properties of a salt, basing this upon where these cations and anions are derived from. And we'll see what we mean by that within our first couple of examples. So, to begin with, let's examine a salt in which the cation is derived from a strong base and the anion would be derived from a strong acid. Now, the most familiar example of this type of species would be the salt NaCl that is essentially table salt. If we consider the components of NaCl, we've got a sodium ion bonded to a chloride ion. And that sodium ion is the cation present in this system, and that sodium ion is also present in the strong base NaOH, that is sodium hydroxide. So we're going to go ahead and call this sodium ion a cation derived from a strong base. And in similar fashion, the anion here is the chloride ion. That chloride ion is also present in the strong acid hydrochloric acid, that is HCl. So that is the salt here, NaCl, would be the salt we would form in an acid-base neutralization reaction between hydrochloric acid, HCl, and sodium hydroxide, NaOH. And as you have probably seen during a titration lab, the solution of salt water that forms from such a neutralization reaction itself is neutral. So that is, the acidity of a sodium chloride solution is neutral, and we can justify that by looking at the potential hydrolysis reactions that would occur between sodium ions and water or chloride ions and water. Starting off here, if we look at a sodium ion interacting with water, if we undergo a hydrolysis reaction here, the products of that reaction would be sodium hydroxide, NaOH, and a hydrogen cation in solution, that is H positive. Essentially here, a single replacement reaction. Now, that being said, this is a very unlikely reaction to occur because if we look at the products that we've formed right there, we've formed, number one, sodium hydroxide, an incredibly strong base, and number two, the hydrogen cation, H positive, which again is the strongest acid that can exist within an aqueous solution. So in all likelihood, forming both a strong base and a strong acid in solution as a product of a reaction is a very unlikely event, given that the reverse process is so incredibly favorable. That is, hydroxide ions and hydrogen ions combine very favorably to form water. So as such, the likelihood of this hydrolysis reaction occurring is very, very low, which essentially means the sodium cation has no appreciable acidic properties in solution. A similar justification here can be made now with the chloride ion. If we write a hydrolysis reaction between the chloride ion and water, recall the chloride ion is the conjugate base of hydrochloric acid. So as such, if we're writing a reaction showing chloride ion acting as a base, we would accept a proton from water, forming as products then HCl and OH negative. And yet again, we see here that those two products are particularly unlikely to form. Again, as hydrochloric acid is a very strong acid, the hydroxide ion is an incredibly strong base, which means essentially all of that hydrochloric acid should deprotonate and donate those protons to the hydroxide ions, meaning the reverse reaction here is incredibly, incredibly favorable and essentially will occur to completion. So long story short, the chloride ion is an incredibly weak base as it is the conjugate base of a very strong acid. So as neither the sodium cation nor the chloride anion has an appreciable ability to act as an acid or a base, we'd expect the overall resulting solution to remain neutral. Now, that being said, that's a very different situation than if we react a cation derived from a strong base with an anion derived from a weak acid. A great example of this type of species would be the species listed there for you, which is sodium acetate, that is NaCH3CO2. Now, as we saw above, the sodium ion is a cation derived from sodium hydroxide, that is a strong base. And again, that sodium cation will not be able to meaningfully undergo a hydrolysis reaction for the same reason we discussed above. The acetate anion, however, in this system itself is the conjugate base of acetic acid that is a weak acid. And as such, the acetate ion is a relatively strong conjugate base. And as such, we would expect to see a favorable hydrolysis reaction in which the acetate ion accepts a proton from a water molecule, forming as products acetic acid, CH3CO2H, and a hydroxide ion, OH negative. Now again, because this acetate anion is a relatively strong conjugate base, we'd expect this reaction to produce meaningful amounts of hydroxide ions in solution, and as such, the acidity of the resulting solution of sodium acetate would be fairly basic. Now, the opposite scenario will likely take place if we switch things up here and have a salt in which the cation is derived from a weak base and the anion is derived from a strong acid. An example of that particular species would be something like, let's say, ammonium nitrate, that is NH4NO3. Starting off looking at the cation here, that cation is the ammonium cation, NH4 positive, which itself is the conjugate acid of ammonia, ammonia being a weak base. And as such, that ammonium cation is a relatively strong acid, a good proton donor in solution. So if we take that ammonium cation and show a hydrolysis reaction here, that ammonium cation can donate a proton to water, forming therefore a hydronium ion H3O positive and ammonia NH3. And again, as a relatively strong acid, that would be a favorable process to occur, generating some excess hydrogen in solution. Conversely, the nitrate ion, NO3 negative, is the conjugate base of nitric acid, and as we've seen before, conjugate bases of strong acids are very, very weak bases, and as such, a hydrolysis reaction in which nitrates react to water to form nitric acid and hydroxide ions is unfavorable and will not likely occur. And as such, the solution of ammonium nitrate should generate an excess of hydrogen ions in solution, resulting in an acidic solution overall. So those are the friendly ones to deal with. Last but not least here, what if we have both a cation and an anion derived from weak species, the cation from a weak base and the anion from a weak acid? An example of this would be something like, let's say, ammonium fluoride, NH4F. In this case, we have two potential hydrolysis reactions that could favorably occur within solution. That is, number one, as we just saw, the ammonium cation can donate a proton to water, forming hydronium ions and ammonia. And additionally, the fluoride ion, being the conjugate base of hydrofluoric acid, itself a weak acid, that fluoride ion is a relatively strong conjugate base, and as such, it is good at accepting protons from water molecules, forming therefore hydrofluoric acid, HF, and hydroxide ions, OH negative. So in this instance, we have two hydrolysis reactions which will likely occur, generating both hydrogen and hydroxides in solution. So the answer to whether this solution overall will be acidic or basic really then depends upon whether the ammonium ion, NH4 positive, is a stronger acid than the fluoride ion, F negative, is a base. It comes down to essentially which species is stronger. And we could get a numeric justification for that if we looked at the relative Ka values of the ammonium ion versus the Kb value of the fluoride ion, the conjugate base. So if we look up some actual data here, I can find on a table of Kas a value of 5.6 times 10 to the negative 10th for the Ka of the ammonium ion, NH4 positive. And similarly, looking up data for the Kb of the fluoride ion, F1 negative, I find a Kb value of 2.9 times 10 to the negative 11th. So again, comparing these relative Ka and Kb values, even though neither one of these is particularly strong as either an acid or a base, it appears that the value of the Ka for ammonium ion is larger than the value of the Kb for the fluoride ion, and thus I would expect that the overall acidity of a solution of ammonium fluoride would be slightly acidic. So having now qualitatively examined the acid-base properties of salts, let's go ahead and move on to some examples in which we can make some quantitative calculations. All right, for our first quantitative example here, we're going to look at determining whether a solution of ammonium cyanide, that is NH4CN, is acidic, basic, or neutral, given information about the Ka of hydrocyanic acid, that is HCN, being 6.2 times 10 to the negative 10th, and the Kb of ammonia is 1.8 times 10 to the negative 5th. Now in particular, I want you to look at the given information in this problem. That is, we have provided you here with Ka not of the cyanide ion, which is present in NH4CN, but instead of the conjugate acid of that cyanide anion, that is HCN. And similarly, again, we have the ammonium ion present in the species NH4CN. That ammonium ion is the conjugate acid of ammonia, for which we have information about its Kb. So essentially here, we have information about the conjugate species rather than the actual dissociated ions that would exist within a salt solution of ammonium cyanide. And as such, the first step we need to do here is to determine the Kb value for the cyanide ion, Cn negative, and the Ka value for the ammonium ion, NH4 positive. Now, you may recall from our previous conversation that if you want to look at the Ka and Kb's of the relative conjugate acid-base species, the product of the Ka of an acid times the Kb of its conjugate base always equals Kw. And as such, I can manipulate that equation in order to solve for the Ks of the conjugates here. Starting off with our base, finding the Kb of that cyanide ion, I'm going to rearrange my equation here. Kb would be equal to the Kw, that is the autoionization constant of water, divided by Ka, which would be a value of 1.0 times 10 to the negative 14th for the Kw, divided by our given value of Ka for hydrocyanic acid of 6.2 times 10 to the negative 10th. And a real quick bit of math here will determine the relative Kb value there is 1.6 times 10 to the negative 5th for the cyanide ion Cn negative. Now a similar manipulation will allow me to solve for the Ka value of the cation present here, that is NH4 positive. So again, rearranging my equation, the Ka value would be equal to the autoionization constant Kw divided by the Kb of the conjugate base, which gives me here 1.0 times 10 to the negative 14th, divided by the Kb of 1.8 times 10 to the negative 5th, that is the Kb of ammonia, yielding then a Ka of 5.6 times 10 to the negative 10th for the Ka of the ammonium ion NH4 positive. So at this point, I now know both the Kb of the cyanide ion of 1.6 times 10 to the negative 5th, the Ka of the ammonium ion is 5.6 times 10 to the negative 10th, and quantitatively comparing those two values, I notice that the Kb of my conjugate base, the cyanide ion, is orders of magnitude larger than the Ka of the ammonium ion NH4 positive, implying therefore the cyanide ion is a stronger base than the ammonium ion is an acid, and as such, I would expect the overall solution of ammonium cyanide to be a basic solution. All right, so this brings us now to the point where we're going to look at calculating the pH of a solution containing a dissolved salt. I've given you a sequence of steps here to follow as we approach these problems because they're going to look a little bit different than the pH calculations you've done for a standard weak acid or weak base solution. And in terms of the sequence of steps, what I want you to consider primarily is what are the major species in solution that are going to either have acidic or basic properties. So things I'd like you to do is, number one, to write a dissociation equation showing the salt dissolving into solution. Once you have determined which ions are present in that solution, figure out which of those dissolved ions would then either exhibit acidic or basic properties. Having identified the species which are either going to be acidic or basic, at that point you're going to write a hydrolysis reaction showing the interaction between the dissolved ion and water, which is either going to produce either number one, hydronium ions, or number two, hydroxide ions. And at that point, you can go ahead then and solve an ice table to determine the equilibrium concentration of the relevant ion in solution, either hydrogen ion or hydroxide ion. So with that kind of general framework we're going to follow here, let's go ahead and work an example problem. This is example number 4, in which we're going to ask you to calculate the pH of a 0.30 molar solution of sodium fluoride, NaF. And you'll see here that I'm giving you one additional piece of information, which is that the Ka of hydrofluoric acid, the weak acid HF, is 7.2 times 10 to the negative 4. So, following our sequence of steps we've given you above there, let's start by writing the dissociation equation for our salt NaF. As sodium fluoride dissolves in water, we see that those polar water molecules exert strong ion-dipole interactions to attract those oppositely charged sodium ions and fluoride ions, causing them to dissociate in solution from one another. So our equation of NaF disassociating here into Na positive ions and F negative ions represents the dissociation equation for this process. Now that we have disassociated those ions from one another, let's consider whether any of them have either acidic or basic properties. Starting off with that sodium ion, we recognize that the sodium ion itself is the conjugate acid of sodium hydroxide, itself a very, very, very strong base. And as such, the sodium ion is going to be an incredibly weak acid and therefore is not going to contribute to the acidity or basicity of our solution, so we can safely ignore it. Conversely, the fluoride ion itself is the conjugate base of hydrofluoric acid. And as such, that fluoride ion is going to be a relatively strong base, meaning this is the one that we have to watch out for. The fluoride ion is going to make our solution basic overall. So I'm going to expect to find here a basic pH when all of this comes out in the end. So now that I've identified that fluoride ion as the ion we need to pay attention to, let's go ahead and write a hydrolysis reaction showing the interaction between that fluoride ion and water. So writing this down here, the fluoride ion, F negative, is going to react to water, H2O, in an equilibrium state to form hydrofluoric acid, HF, and the hydroxide ion, OH negative. Again, that fluoride ion is picking up a hydrogen off of water, and in doing so is acting as a base. So I've got the applicable reaction now for a hydrolysis equation. At this point, we're going to go ahead and set up our ice table to calculate our concentration of the hydroxide ion in solution. So setting up the ice table here, let's plug in the information which we currently know. Recognizing that sodium fluoride dissociates in a 1-to-1 molar ratio to form fluoride ions, that implies I will have initial concentration of fluoride ion of 0.30 molar in my solution. We can safely ignore water because, again, this is a liquid phase species and thus exists at relatively constant concentration. And we're going to assume initial concentrations of both HF and of the hydroxide ion OH negative of zeros. My changes in concentration here will be a minus X for the fluoride ion, a plus X for hydrofluoric acid, and a plus X for the hydroxide ion, leaving me with equilibrium concentrations of 0.30 minus X for the fluoride ion, and then X and X for hydrofluoric acid and the hydroxide ion, respectively. So we've got an ice table. You can probably see where this is going to go from here. Let's go ahead and write our K expression that governs this equilibrium. This is going to be now a Kb, as the fluoride ion is acting as a base. Products over reactants gives me the concentration of HF times the concentration of OH negative divided by the concentration of the fluoride ion F negative. Now, unfortunately, I was not given a Kb for the fluoride ion. Instead, I was giving the Ka of hydrofluoric acid. So a real quick manipulation here will allow me to solve for the Kb of the fluoride ion, that being the conjugate base of hydrofluoric acid. The Kb of the fluoride ion would therefore be equal to autoionization constant Kw divided by the Ka of its conjugate acid. So I have 1.0 times 10 to the negative 14th divided by the Ka of HF, which was given to me as 7.2 times 10 to the negative 4th. And a quick calculation there will yield a Kb for the fluoride ion I get of 1.388 times 10 to the negative 10th for that Kb. So I'm going to go ahead and carry that over now into my expression for that we have previously formulated here. And this gives me now the Kb value of 1.388 times 10 to the negative 10th is equal to now my equilibrium concentration of HF times OH negative, which is going to be then X times X for X squared in the numerator, divided by the equilibrium concentration of the fluoride ion, which we had from our ice table as 0.30 minus X in our denominator. Now, recognizing that this is a very small value of Kb, that implies that the assumption method will be valid to solve here for X. I'm going to go ahead and make the assumption that X here is very small compared to the initial concentration of 0.30, which simplifies my expression now to the Kb value of 1.388 times 10 to the negative 10th is now equal to X squared divided by 0.30. Solving for X from here, I'm going to multiply both sides by 0.3 and take the square root of both sides. This yields, therefore, an X value of 6.45 times 10 to the negative 6th molar for this system. And again, because I did make an assumption to make sure we're keeping things tidy here, I will check that assumption. The x value of 6.45 times 10 to the 6th divided by the value we assumed is small compared to of 0.30. Multiplying that by a factor of 100 yields a percent error here of 2.2 times 10 to the negative third percent, well within our 5% boundary here, so this is therefore a valid assumption. All right, so considering now what I've just found, I now know the concentration of hydroxide ion for this system in equilibrium is equal to X of 6.45 times 10 to the negative 6th molar. I can then find the pOH of the solution by simply taking the negative log of that value. So the negative log here of 6.45 times 10 to the negative 6th yields a pOH of 5.19. And real quick cleanup here then to find my pH, which we were asked for, I will then subtract 14 minus my pOH. So 14 minus 5.19 yields therefore a pH of this solution of 8.81. And that being said, this makes a lot of sense as we had predicted because the sodium fluoride solution containing the relatively strong conjugate base fluoride ion would therefore be a basic solution overall. All right, and that's how you solve a pH of a salt solution problem. We'll move on to one final example. All right, for our last example for this particular lecture, we are going to be looking at a type of question the AP test likes to ask you in order to compare the acidity or basicity of a number of different chemical species. So what they're essentially going to ask you to do here is to list in order a number of different species from either most acidic to most basic or most basic to most acidic. And in order to correctly identify the order here, a couple things we're going to consider. Number one, we want to think about the identities of any known strong acids or bases which are present among the species listed. That's going to be the first thing that we can do to kind of eliminate the outliers to make the rest of it a little bit easier for us. Once we've eliminated those strong species and placed them in the appropriate orders, at that point we need to think about the component ions present in each species which might exhibit either acidic or basic properties, while at the same time considering if there are any weak species present that we might be familiar with from our general knowledge. So, long story short, let's go ahead and take a look at the example here. We're going to try to order here the species KOH, that is potassium hydroxide, KCl, potassium chloride, KCN, potassium cyanide, NH4Cl, that is ammonium chloride, and HCl, hydrochloric acid, in order from most acidic to most basic. Now to begin with here, let's go ahead and take a look at the species here and see if we can identify the presence of any strong acids or bases present. The first of our listed species, potassium hydroxide, is an alkali metal hydroxide, and as such, this is a strong base. It is the only strong base listed out of that set of 5, so I'm going to go ahead and immediately place that one down at the most basic end of our list. KOH goes at the very bottom. Now, conversely, looking through here at the very end of our list of 5 here, I have HCl, that is hydrochloric acid. Hydrochloric acid is one of these strong acids we asked you to memorize in an earlier lecture here. And as such, I'm going to go ahead and list hydrochloric acid at the top here as the most acidic species present. And that really now leaves us with 3 species, that is potassium chloride, KCl, potassium cyanide, KCN, and ammonium chloride, NH4Cl, that remain to be placed in order. So let's go ahead and look at these 3 species together. First off, potassium chloride, KCl. Potassium chloride is a salt which would be formed by the neutralization reaction between potassium hydroxide, KOH, and hydrochloric acid, HCl. As the potassium ion there is the conjugate acid of the strong base potassium hydroxide, that makes the potassium ion an incredibly weak acid which will not therefore have meaningful acidic or basic properties. Alternatively, the chloride ion here is the conjugate base of the strong acid hydrochloric acid, and as such, the chloride ion is an incredibly weak base. So really, potassium chloride, the component ions here are neither going to exhibit either acidic or basic properties, which means potassium chloride is going to be very much a neutral salt. So having now identified potassium chloride as a neutral species, let's move on to potassium cyanide. Potassium cyanide is a salt which will be formed from, again, the reaction between potassium hydroxide, a strong base, and now hydrocyanic acid, HCN, a weak acid. And again, the same is true of the potassium ion as in the previous example species. That is, it is the conjugate acid of a strong base and therefore an incredibly weak conjugate acid. The cyanide ion, however, present here is the conjugate base of a weak acid, and as such, it is a relatively stronger base. So I would expect, therefore, potassium cyanide to be a basic species in solution due to the presence of the conjugate base Cn negative. So this one's going to lie on the more basic end of the spectrum than potassium chloride, a neutral species. Our last remaining salt here is ammonium chloride, NH4Cl, which upon dissociation into solution will form ammonium ions and chloride ions. Now, ammonium chloride is the salt that would form in a reaction between the weak base ammonia and the strong acid hydrochloric acid. And again, because the chloride ion is the conjugate base of a strong acid, that would imply, therefore, the chloride ion is an incredibly weak conjugate base, so it's not going to contribute meaningfully to a change in pH of our solution. The ammonium ion, however, is the conjugate acid of ammonia, itself a weak base, and as such, the ammonium ion is a relatively stronger conjugate acid. So therefore, upon dissolving in solution, the ammonium ion will donate protons to water, and as such, produce an excess of hydronium ions in solution, making a solution of ammonium chloride somewhat more acidic. So I can again now order the remaining species here. I'm going to go ahead and put potassium chloride right there in the center as a neutral species. The potassium cyanide, KCN, is going to be on the more basic end of our spectrum here, as the cyanide ion is the conjugate base of a weak acid. And then last but not least here, the ammonium chloride is going to go on the slightly more acidic end of our spectrum due to the acidic nature of the ammonium ion, that conjugate acid of a weak base. So, by applying essentially all of our knowledge about the behavior of not only strong and weak species, but also of salts which contain ions which can act as either acids or bases, we can effectively arrange these in order of their nature from most basic to most acidic. All right, that is it for our discussion of the acid-base properties of salts and other lectures. We'll see you at the next one. Thanks for listening.